Computing the 2's complement in fixed-bit binary. In this video, I will show you how to compute the 2's complement in fixed-bit binary. In the next video, I will show you how to use the 2's complement in fixed-bit binary to represent negative numbers and perform subtraction. In this example, we'll determine the 2's complement of 101101 in 6-bit binary. What I like to do when I teach this to students is I like to start off by actually writing little squares for the bits. So 6-bit binary would have 6 little squares, each representing a bit. So this binary numeral 101101 I would put into these little squares to represent each bit. 101101. Now this idea emphasizes the fact that in, for example, and this is just an example, 6-bit binary, we only have 6 bits. We don't have 7 bits. We don't have 8 bits. We have only 6 bits. And so this is very, very important. And in fact, this is why this whole 2's complement thing really works so well in this particular application that you'll actually see fully embodied in the next video. So step 1 is to determine the 1's complement. Now, the word complement in mathematics is always used in the same way. It's often expressed as not, or the negation of something, or everything that's not what you see but is in the universe. So the 1's complement is clearly consistent with that definition. All the 1's complement means is that we interchange the bits. Or really, we interchange the 0's and 1's. So the 1's complement of this, now notice I'm writing out the 6 little boxes for each bit to emphasize the fact that there are exactly 6 bits. That's the idea of fixed bit. So this 1 has to be a 0, but this 0 has to be a 1. This 1 is now a 0. This 1 is now a 0. This 0 is now a 1, and this 1 is now a 0. So every 1 is changed into a 0, and every 0 is changed into a 1. So this could be considered like a negation, but this is a complement. This is the 1's complement. But step 2, which is the last step in getting the 2's complement, is to add 1 to the 1's complement. So the way I teach this again is to emphasize that this is 6 bits. I'm actually going to write 1, 2, 3, 4, 5, 6 squares here. 1, 2, 3, 4, 5, 6 bits here. And we only have 6 bits for our answer. So I want to emphasize the fact that this addition has to be in 6 bits. So what we do, because that's the example, it could be in any fixed bit size, but we're doing 6 just as, an example here. So I'm going to take the 1's complement and write it over again. So we have 0, 1, 0, 0, 1, 0. And that's this. And again, this is the ones complement. And then it says, to get the twos complement, we add 1 to the ones complement. So we just add 1, and these are all zeros. You don't have to put them in, but I put them in to show, the student exactly what we're doing. And so we just take 0 plus 1 is 1, and 1 plus 0 is 1, and 0 plus 0 is 0, and 0 plus 0 is 0, and 1 plus 0 is 0, and 0 plus 0 is 0. And this is your answer. This is your twos complement. And this is your final answer. So let's do an example, another example. So here, let's determine the twos complement of 5 base 10 in 7-bit binary. So what I'm going to do is I'm going to start off by writing my 7 bits as little squares. So we have 1, 2, 3, 4, 5, 6, 7. And the place value system, I'm going to put in 1, 2, 4, 8, 16, 32. Now this bit over here is called the leading bit. And I'll always write the leading bit as LB. You don't give the leading bit a place value in this fixed bit binary because it serves a purpose that I haven't shown you yet, but I will. So if we want to encode 5 base 10 in 7-bit binary, we're going to see here, we're going to take a 4 and a 1 is 5, and everything else is 0. Right? So this is 5 in binary. Right? So this is really step 1. Which is just encoding this 5 into binary. But we don't want 5, we want the twos complement of 5 base 10. So the next step is to get the ones complement. So I'm going to write out my bits. And this is step 2. And that's the ones complement. So we're just going to interchange all the bits. So we have 1, 1, 1, 1, 0, 1, 0. And that's the ones complement. Step 3. We add 1 to get the twos complement. All right, so that's the next step. And so I'll do this here. So we take the 1, 2, 3, 4, 5, 6, 7, the bits. 1, 2, 3, 4, 5, 6, 7. Plus, and we only get 7 bits in our sum because we are only working in 7 bits. So 1, 2, 3, 4, 5, 6, 7. And so we take the ones complement, which is 1, 1, 1, 1, 0, 1, 1, and we add 1 to this. Wait, did I copied down? No, I think I copied down. I'm sorry, I copied down the wrong one. This should be 1, 0. Make sure I copied this down, right? 1, 1, 1, 1, 1, 1. It should be. And then 0, 1, 0. Okay. All right. And so then we add 1 to this. And I always like to put the zeros in, even though you know that they are 0. I still like to put it in. And so we get 1, 1, 0, 1, 1, 1, 1. So that is the 2's complement of 5 base 10 in 7-bit binary.